Revising Atoms and Elements, Part 5, Writing Equations for Chemical Reactions. Okay, so in a chemical reaction, something has actually changed into something else at a molecular level. We're going to have a chemical reaction take place in our test tube on the board, and then we're going to write the equation that goes with it. So first of all, into the test tube, some sulfuric acid. Okay, so there it is. That's our sulfuric acid. And we write sulfuric acid as H2SO4. And what this means is that a molecule of sulfuric acid is made up of 2 hydrogen atoms, 1 sulfur atom, and 4 oxygen atoms. So obviously sulfuric acid is a compound. It is a mixture of different types of atoms. Okay, to our sulfuric acid, we're now going to add a small strip of magnesium. Okay, so here's our magnesium. And since we've added it to the sulfuric acid, we'll write that as such. Okay, so magnesium added to sulfuric acid. Almost immediately, we're going to see something happening. Here, we can see there are some bubbles coming up through the liquid. Now, when we put the sulfuric acid into the test tube, it was a liquid, and at room temperature, it would stay as such. And when we put the magnesium into the test tube, it was a solid, and at room temperature, it should stay as such. So if there is now a gas in the liquid, it means that some part of the liquid and some part of the solid has mixed together and made a new substance that is a gas at room temperature. But what is this gas? Well, let's start with what gases we know about. How about carbon dioxide? Well, the formula for carbon dioxide is CO2. This means that a molecule of carbon dioxide has 1 carbon atom and 2 oxygen atoms in it. Okay, well, can we make carbon dioxide out of the building blocks we've already put into our test tube? Well, we can use 2 oxygen atoms from the sulfuric acid because sulfuric acid's got 4 oxygen atoms in each molecule. But what about the carbon? No, there's no carbon anywhere in our test tube. So we can't have carbon dioxide coming out of it. Okay, so our only 2 choices really are oxygen and hydrogen. And there's a very, very easy test to see which is which. And both require a splint and a flame. Oxygen is needed for fires. So if I take my splint and I blow out the flame, if the gas in the tube can reignite the splint because it still has heat and it has fuel, then the gas is oxygen. But this gas doesn't relight my splint. That means it's not oxygen. So what's the test for hydrogen? Well, hydrogen is an extremely flammable gas. So if I relight my splint and bring it to the top of the test tube, then if it's hydrogen, then the very distinctive pop sound will give it away. Yes, definitely hydrogen in this tube. So in the tube, we started with molecules of sulfuric acid and molecules of magnesium. Now the hydrogen has separated. So when we write the products of this chemical reaction, we write the hydrogen separately. So what's been left in the test tube? Well, everything that didn't just come out as a gas. So we've got the sulfate here and the magnesium here, and they've actually joined together to form a new molecule called magnesium sulfate. As you can see, though, everything that was in the test tube to begin with has come out at the end. Nothing new's been created that wasn't already there, and nothing's disappeared. The only thing that's changed is the way in which they're connected to each other. Now, this sort of reaction is actually called a displacement reaction because the magnesium has displaced the hydrogen and taken its place. Can you see that? Imagine that this is a school dance and hydrogen has gone to the school dance with the sulfate. Magnesium has gone to the school dance on its own. But once there, something happens on the dance floor, and when you see them leave, hydrogen's leaving on its own and the magnesium has coupled up with the sulfate. It has literally pushed the hydrogen out of the mix because it's much, much more reactive. Now you can make predictions on what's going to happen in a chemical reaction if you know how reactive the reactants are to begin with. And this is where the reactivity series comes in. The elements in the reactivity series have been ordered by how reactive they are, with the most reactive elements at the top. As you can see, potassium is at the top of this series and platinum is at the bottom. Everything that is higher than hydrogen on this series is going to react with an acid. And here's magnesium, much, much higher than hydrogen, and therefore going to be able to displace hydrogen from any acidic solution. All right, so here's another one. I've got two test tubes here, and into the first test tube I'm going to put a solution of copper sulfate. The formula for copper sulfate is CuSO4, which means in every single molecule of copper sulfate there's one copper atom, one sulfur, 4 oxygen atoms. In the other test tube I'm going to put a magnesium sulfate solution. Now if copper sulfate is CuSO4, can you work out what magnesium sulfate might be? Here's its formula, MgSO4. Now into the copper sulfate in the first test tube I'm going to add a strip of magnesium. How would I write that in as part of the equation? Well, I'm literally going to write plus Mg. Simple as that. Into the second test tube I'm going to add some small bits of copper filings. So the reactants in the second test tube is MgSO4 plus Cu. Now, using the reactivity series, can you predict which, if either of the test tubes, a chemical reaction is going to happen in? Let's have a look at the reactivity series again. Well, here's copper on the series, and there's magnesium. Magnesium is much, much more reactive than copper. That means it can displace copper from a compound. So let's go back and have a look at our equations again. In the first test tube, copper is part of a compound with sulfur and oxygen, and magnesium is on its own. In the second test tube, it's the magnesium that's part of a compound with the sulfur and the oxygen, and copper is on its own. I'll give you a hint. A reaction is only going to happen in one of these test tubes. Which one? Well, if you guessed this one, you would be right. The magnesium is already starting to dissolve. And look at the bottom. We can see the copper coming out. Now, at room temperature, copper is a solid, so it's being deposited at the bottom of the test tube. Have a go at writing the products for that first chemical reaction. We can see that the copper is now on its own, and the magnesium has taken its place as becoming part of the sulfate solution. So here we go, the copper is on its own. So there it is. And in that test tube, we now have magnesium sulfate. Well, what about this second test tube? Well, if we look, nothing is happening. And that's because the copper is not reactive enough to displace the magnesium. It can't do it. And this is why we use copper in lots of our pipes for water and electricity. Because copper cannot react with things very easily. It's not going to rust or corrode over time. It also means that there's no chemical reaction taking place in the second test tube. Now, these are nice, easy equations to figure out because, as we can see, one molecule of copper sulfate with one molecule of magnesium gives us one molecule of copper and one molecule of magnesium sulfate. Everything balances and pairs up nicely. But it's not always that simple, as we're going to see when we try to make water. In the first test tube, I've got a chemical reaction happening that's letting off hydrogen gas, and I'm collecting that in my balloon. Now I've got lots of helium in my balloon. I'm going to stretch it over the second test tube that is currently releasing oxygen due to a different chemical reaction. Now, at the moment, I haven't got water in my balloon because the hydrogen molecules and the oxygen molecules haven't actually reacted together. It's more of a mixture in there of hydrogen and oxygen, all happily ignoring each other. But if I take this balloon off the test tube and then add a flame to it, we're going to get a very big bang indeed, as those oxygen molecules are split apart and join up with the hydrogen molecules. Water. We've just created water. But how would the chemical equation go for that? Let's have a look. Well, the product of the reaction was water, and water, we know, is written H2O. So as a molecule, it has two hydrogen atoms and one oxygen atom joined together. Well, what did we start with? We started with hydrogen and oxygen. And hydrogen always travels around in pairs, as does oxygen. So a molecule of hydrogen, here it is, and a molecule of oxygen. And they're joined together. But does this really add up? Well, I've got 1, 2 hydrogens on this side, and I've got 1, 2 hydrogens on that side. So the hydrogens all balance. What about the oxygens? Well, I've got 1, 2 oxygens on this side, but only 1 oxygen on that side. That doesn't balance. That means there must be an extra oxygen out there. Well, can we just add it on to the end? Well, that looks balanced, but unfortunately it doesn't work because oxygen cannot travel round on its own. Therefore, at the moment, this is unbalanced. How are we going to rectify this? Well, every time we have one oxygen molecule, we get 2 oxygen atoms. And each oxygen atom needs a pair of hydrogen atoms. So if we've got 2 oxygen atoms, we need 2 pairs of hydrogen atoms. Let's get those on the page so we can see them. Here's another pair of hydrogen atoms. Because hydrogen travels around in pairs, it's an extra molecule. That now gives us 1, 2 molecules of hydrogen, and we write that with a large number 2. So large number 2 for the number of molecules, small number of 2 for the number of atoms in each molecule. Now, how does this balance up on the other side? Well, I've got my 1, 2, 3, 4 hydrogen atoms on that side, which means I now need another 2 on the other side to keep it balanced. 1, 2. So that's 1, 2, 3, 4. And they both want to join up to an oxygen atom, which gives us 1, 2 oxygen atoms on the other side, the same that we had to start with. Brilliant. So that's all balanced. 4 hydrogen atoms at the start, 4 at the end, 2 oxygen atoms at the start, 2 at the end. And that's made not 1, but 2 molecules of water. So we're going to put a giant 2 on the front here. Now, if you can explain why molecules of water always get made 2 at a time, then I think you've got a pretty good understanding of both writing and balancing equations. End of part 5.